Hey everybody, we're back with part 2 of the derivatives of trig functions. You have this packet here to fill out, and what I've done here for numbers 1 to 6 is I've recopied in all of the rules that we established in the first video. So if you want to pause this video and fill these out, these are the derivatives of your 6 trig functions. I've also written down a helpful trig identity that we also reviewed in the last video, and that's just your Pythagorean identity. Cosine squared x plus sine squared x is equal to 1. Reason why is right here. Every x coordinate on the unit circle is given by cosine x. Every y value is sine x, or if you're doing theta, cosine theta and sine theta. And the radius of the unit circle is 1. So by Pythagorean theorem, this over here holds true. So I'm just reminding you of that. And now we can just get into examples. So take a look down here at example 1. It says, given y, we're to find the derivative of y with respect to x. So if you look at this problem, y equals x squared times sine x. So you see the trig right there. But what's interesting is the overriding rule here is product rule, because you have a u here times a v. So we're going to have to run the product rule, and then within it, we will use the trig rule number 1 up here. We'll have to take the derivative of sine. Okay? So let's run that product rule. So the product rule would say dy dx equals the first. So I'm going to bring x squared down times the derivative of the second. Well, the derivative of sine is cosine. Plus the second, which is sine x, times the derivative of the first, which is 2x. So cleaning this up, and the reason I like to clean these up, I never want you to think back here that you should multiply this x with this 2x. The sign is only pertaining to this x, and the whole thing is being multiplied by 2x. So let's write the final answer in a less confusing way. Let's say x squared cosine x plus 2x sine x. That's a nice final answer. Okay, flip it. Number 2, example 2. Given y, find dy dx. Now, you got some trig going on here, clearly. But more than that, you have a quotient rule. So the overriding rule is the quotient rule. Within the quotient rule, you'll have to look back at your derivatives for sine and cosine. Okay, so here we go. Dy dx equals. Okay, the quotient rule says you take the denominator. So 1 minus the sine of x times the derivative of the numerator. The derivative of cosine x is negative sine x. Minus the numerator times the derivative of the denominator. Now, the derivative of 1 is 0. The derivative of sine x is cosine x, but because we have the negative, we'll bring that along and call it negative cosine x. So it's kind of like 0 minus cosine x, or negative cosine x. And this is all over the denominator squared. Okay, so let's see if we can clean it up. Looks like I can do some distributing here. I can take the negative sine x and multiply it into this binomial. So negative sine of x times 1, negative sine x. Negative sine x times negative sine x is a positive sine squared x. A negative cosine x times a negative cosine x is a positive cosine squared x. And this is still all over 1 minus the sine of x squared. Okay, right here in the numerator, do you see it? You have your Pythagorean identity. This is 1. So I'm going to rewrite the numerator as 1 minus sine x. I could do negative sine x plus 1, but based on where I'm headed with this, I'm going to do 1 minus sine x over. And on the denominator, I'm actually going to write this out twice. 1 minus sine x times 1 minus sine x. So my final answer, 1 minus sine x on the top can cancel out 1 minus sine x on the bottom, leaving me with a final answer of 1 all over 1 minus the sine of x. And that's going to be dy dx. Final answer. So that one was a little bit more involved. You had the quotient rule, the trig, the identity, the simplification. So some of these get a little bit more involved. Okay, let's take a look at example 3. They want us to go even further on this one. Oh, pardon me. Hey, Bob, I'm making a video. Can I call you right back? Okay, let me call you right back. Okay, bye-bye. Oh, Mr. Capilupo. Okay, I'll call him back. So, this is what happens when you make videos at school. Okay, example 3. Write the equation of the tangent line to the curve y equals cotangent x at the point pi over 4, 1. Okay, so not only are we going to have to find the derivative, which is going to help to get us the slope of the tangent line, we're then going to have to find the slope of the tangent line at this specific point, and then we're going to have to write the equation of that tangent line. So you know me, Miss Callahan is visual, so the very first thing I'm going to do, without even a question, is I'm going to graph y equals cotangent of x. Y equals cotangent of x. So I'm actually just going to do this on my TI-84. You probably graphed cotangent of x by hand in pre-calculus, but let's use some of our technology here. Okay, let's sketch this graph. So I'm going to, okay, cotangent. Well, I don't have a cotangent button, but cotangent is the same as, well, it's the reciprocal of tangent, or I could think of it as cosine over sine. But why don't I just, it'll be easier if I just put it in as 1 over the tangent of x, right? Okay. Now, let me tweak my window. Based on those graphs we were doing the other day with the sine and the cosine, I'm kind of thinking I'll just do like a full cycle of cotan. So maybe I'll go from 0 to 2 pi on the x, and I will adjust my scale to increment by pi over 2. Okay, and I'll hit graph. So here's what we're looking at. Now you see the cyclical periodic nature of this because the cotangent, just like anything else on the unit circle, is going to keep repeating itself as you go further and further out. So this looks like 2 cycles of cotan. So I'm just going to kind of copy this onto my paper. So got my y-axis, got my x. This is x and y. And I look to have a vertical asymptote here at 0 and at pi. So I'm going to put a vertical asymptote here at 0. And then I'm going to come pi over 2, and then pi, vertical asymptote, and then 3 pi over 2, and then I'm thinking 2 pi is going to have a vertical asymptote. And then in between, we've got these curves that sort of repeat themselves, coming down, down, and so forth. So this is my graph of a few cycles of cotangent x. Now here's what's really interesting. If you were to rewrite cotan x as cosine x over sine x, and you wanted to know where these vertical asymptotes are, if you set the denominator equal to 0, sine x equals 0, and then think about your unit circle, well, where is the second coordinate 0? Well, here at 0, and here at pi. So it makes sense that your vertical asymptotes are at 0, pi, 2 pi, 3 pi, 4 pi, increments of pi. Okay, and then what's happening in between as we work around the circle is that the cotangent is, you know, some positive, less positive, less positive, and then turns to be negative. Makes sense because once you get over here to the second quadrant, your coordinates are both positive and negative, and a positive divided by a negative is a negative. So it makes sense that after you cross over pi over 2, that you are now dealing with negative values. So there's ways you can connect this, so that's good to get an idea of that. Now, we're going to go to the point pi over 4, 1. And I know that that point works because if I would go to pi over 4 on the unit circle, I know the coordinates there are root 2 over 2, root 2 over 2. And so the cotangent at pi over 4, if I take the cosine divided by the sine, I get 1. So it makes sense that the cotangent of pi over 4 is equal to the cosine at pi over 4 divided by the sine at pi over 4, and that's 1. So this point makes sense to me, and more than that, if I go to the graph, pi over 4, 1 is right here. So if I draw a tangent line there, this is what I'm looking for, the equation of that tangent line. Okay, so let's get into it. So let's come down here. We start with y equals cotan x. Now, since we need the slope of the tangent line, we are going to need the derivative. And we have that right here on the front page. The derivative of the cotangent of x is the negative cosecant of x squared. So I'm going to write it like that, negative cosecant x squared. And what I really love about this and this graph is you can see that every slope on this graph is negative. You have a strictly decreasing function. Look at this. It's always decreasing. No matter where you go on this curve, the slope will be negative. So the slope here makes sense. So now I've got the slope of the tangent anywhere I want to go. I want to go to x equals pi over 4. So I'm going to plug pi over 4 in here. So negative cosecant of pi over 4 squared. So I've got to evaluate that. Now let's think about pi over 4. Okay, so we have the coordinates here at pi over 4. Cosecant of pi over 4 is the reciprocal of sine. So I've got to take my sine, which is root 2 over 2. I've got to flip it over or reciprocate it, square it, and then apply the negative. So this is going to give me negative 2 squared is 4, and square root 2 squared is 2. So my slope is negative 2. So the slope of this tangent line right here that I drew at pi over 4, 1, right here, is negative 2. So now I come over and write the equation mx plus b. Remember, this is m, so negative 2x plus b. And now I just filter in my point, xy. So y is 1, and x is pi over 4. And so solving now for b, I have 1 equals negative 2 times pi over 4 is negative pi over 2 plus b. So b will simply be 1 plus pi over 2. And you can get that as a decimal if you want, or leave it exact like this. So the final answer, final answer to this problem, equation of the tangent line is, drum roll please, y equals negative 2x plus 1 plus pi over 2. That's my b. There you have it. Hope that made sense. Thanks for watching.